I am from the Tensilica Vision and AI group at Cadence. Today we will talk about Cadence Tensilica Edge AI Processor IP solution for broad market use case. We are in the business of providing processor and DSP IP. Our customer ships over 7 billion processor annually. We are number one in DSP IP licensing revenue and number two in processor IP licensing revenue. We are number one supplier of Vision DSP and audio and voice DSP. 19 out of top 20 semiconductor vendors use Tensilica product. We have over 200 ecosystem partners and over 300 licensee. Today we will focus on voice and vision AI applications. Voice AI is already used on various edge applications like smartwatch, mobile phone, smart speakers, and hearables. Vision AI is already used in mobile phones, AR/VR platforms, smart surveillance, and autonomous vehicles. When we look at edge AI for voice and vision, we will typically see the below flow. There is usually a sensing device like a microphone, an image sensor, or a radar or a LiDAR. After that, you might usually have some type of a pre-processing, followed by an inference AI, and followed by a post-processing. So any sensing application like this always has a pre and a post-processing on top of inferencing AI processing. So in order to get the best solution, one need to solve the whole data path. Here is an example of microphone application. Usually a voice AI you use for noise reduction, voice detection, and speed enhancement. Also, sound analytics is done using some type of AI. Privacy, latency, power, and availability of network drives voice UI and other ML application to edge devices. If we examine the smart speakers, there is a microphone and a speaker. So the smart speaker needs solution for voice, audio, and AI processing. There are various AI workload in the voice path. This could be for some examples like keyword, command recognition, voice enhancement, and noise suppression are AI workload examples. There are various non-AI workloads such as EQ, MPEG decoding, sound decoder, speech decoder, and these are classic audio algorithms. So a smart speaker needs both voice audio DSP and something that can process voice and audio and voice AI. Here is an example of a camera pipeline. Here the information comes from the image sensor, usually what we call a Bayer sensor, followed by a pre-ISP processing where you might do something like a noise reduction, followed by Bayer ISP, so that converts Bayer information to RGB and YUV, followed by a pre-processing where depending upon what you're trying to do, you might do some 2D, 3D noise reduction, high dynamic range processing, you might do image pyramid. And then once you have done this pre-processing, depending upon, again, what network you're trying to run, you might do some classification, object detection, segmentation type of AI workload. And followed by, there is usually some kind of a post-processing where you might do NMS, you might do deblurring. Here again, what application you're trying to do. But as you can see that in this application also, before the AI, there's a pre-processing, and followed in the AI, there's usually a post-processing. This slide, we are showing you various examples where there is a mix of vision and AI. The first example is for face detection. In this situation, before doing a face detection, usually you will run some kind of a multi-scale pyramid to scale the image, which is a classic vision operation, followed by a face detector AI operation. If we look at HDR, you could do a scene detection AI operation, and based on what is being detected in the scene, you might do an HDR processing, and which may be a typical vision operation. If you are doing a bokeh with single camera, in that situation, first you may do a segmentation. That is a classic AI operation, followed by blurring and deblurring, which is a classic vision operation. So in all these use cases, you have mix of vision and AI operation. So one would need both vision and AI processing in the camera pipeline. Let's dig deeper. Let's take a look at a neural network example called MTCNN, which is a face detection neural network. MTCNN uses 3 separate nets, POR. Glue processing is inserted between the nets to perform end-to-end face detection. If the entire networks are sped up, the application speed up will be bottlenecked by the glue processing, which does not need to be standardized. So in this situation, a high-performance DSP targeted vision application is required to keep up with the evolving glue processing requirement. In this slide, we are taking a hypothetical example when convolution is sped. So as you know, convolution is one of the major operation in any neural network. As convolution is sped up, the actual network speed up will vary. Some network will have a modest speed up, bottleneck by other layers. So not necessarily by speeding up convolution, one can increase the performance of the complete full network, because it all depends on how many other layers are there in a neural network. In this chart, we are showing timeline of various networks when they were developed. But on vertical axis, we are showing you the percentage of the layers which are non-convolution layers. Now, depending upon the network, the non-convolution layer can be 20% to as high as 80% of the cycles. A high-performance DSP targeted at an application can keep up with this evolving requirement. So what we are saying that in order to speed up this non-convolution layers, a high-performance DSP is required. So when one is looking at deploying an AI solution for edge AI or embedded system, they will usually look at how flexible the solution is. Is it low power? Does it provide the performance I need? And can I get the solution out in a fast time to market? There's various options. You can do all this thing on a CPU. You could do this CPU plus GPU. You could develop a hardware for your specific neural network. But in order to meet the flexibility, the low power, performance, and time to market, a programmable DSP would be one of the options that can give you a very highly flexible solution, low power, a fairly good performance, and a time to market. Now, if one is looking for a much higher tera-op performance for the neural network, then a programmable DSP with a hardware accelerator could be one of the solutions. So here we are talking about the Tensilica AI portfolio. So Cadence Tensilica offers 2 types of solution for AI at the edge. We have highly flexible multi-use DSPs, and we have best-in-class for low power and high performance AI processor. Our Vision DSP, Vision P6 and Vision Q7 offers Vision plus AI both. So that's they are highly flexible and they are multi-use. and they can offer you a solution up to 1 teraop. Our hi-fi DSPs are highly flexible and can be used for both voice audio processing and for voice AI. DNA, that stands for Deep Neural Network Accelerator, is a highly scalable AI processor. It can provide you a highly scalable solution from half a top to 4 top with a single core and multi-tera ops with multi-core. And it offers the best-in-class power and performance. So let's go a little bit deeper in each of this solution. So Tensilica Hi-Fi DSP is the leading IP solution for audio, speech, and machine learning. Cadence enables developers to train and seamlessly deploy the machine learning application on Hi-Fi DSP using TensorFlow Lite for microcontrollers. Hi-Fi DSP has extensible production-ready software from Cadence, and then the large ecosystem of over 160 software partners. Our Extensa audio framework accelerates integration of ML and traditional audio workload, reducing time to market. Vision DSP. So we offer two Vision DSP, Vision P6 and Vision Q7. These are very highly successful reshipping in various platforms. This DSP offers vision acceleration, AI acceleration, high data throughput, and also libraries and tools. So for the vision acceleration, these are highly programmable VLIW SIMD engine. It offers 8-bit, 16-bit, 32-bit integer processing, single precision, and half precision floating point support. For AI acceleration, this DSP has 256 or 512 8-bit MAC, offering up to 1 top of AI performance. And it also offers half precision FP16 support if our customers want to run AI in the floating point. For the high throughput, it has one of the widest memory bus, 1024-bit memory interface, scatter gather technology, and multi-channel IDMA. In terms of library, we have OpenCV-based imaging and vision library, SLAM library, OpenCL Halide and OpenVX support, and then neural network compiler based on ONNX and GLOBE, and Android Neural Network API for those customers who are using Android operating system. DNA, Deep Neural Network Accelerator. It's a single processor for both vision and AI. It offers a highly scalable solution, as we talked earlier, but one of the most important feature of this IP is sparse compute engine. Sparse compute engine means it avoids multiplication with 0. And because of that, it achieves very high MAC utilization. And because of that, we can achieve a very high TOPS per watt. So DNA IP is built using XNNE plus Vision P6. XNNE stands for Extension Neural Network Engine. So Extension Neural Network Engine has a scalable sparse engine. It's a scalable from 256 MAC to 2048 MAC, offering half a top to 4 top in a single IP and a unified memory buffer. Vision P6, we already talked about, it's a VLIW SIMD DSP, but it's there for future proofing and expanding. So if some new network cannot be supported on the neural network accelerator hardware, then the Vision P6 can be used to run those layers. Also, as we've been talking about, Vision P6 can be used for pre and post processing. And if possible, if not on top of the pre and post processing computer vision, there might be some other CV workload that you want to run in this application, and the Vision P6 can be used for that. So let's examine again the Vision plus AI workload on our Tensilica DNA processor. So pre-processing can be done on Vision P6. So as we were talking earlier, something like a multi-scale pyramid, noise reduction, some color space conversion, any of those operations can be performed on Vision P6. AI workload can run on our neural network hardware, where we offer the highly optimum sparse neural network engine. And then the post-processing again can run on Vision P6 for something like a non-maximum suppression, NMS, deblurring, HDR. Again, it all depends on type of networks that you're running. But some of the example network like YOLO, SSD, Mask CNN have greater than 10% cycle for post-processing. So till now, we have been talking about our hardware IP, but hardware IP without any software has no use. So we offer various software tools for our customer. Our Hi-Fi DSP offers neural network libraries, ANN library, Extensa audio framework, and it supports TF Lite and TF Lite Micro. On our Vision DSP and on DNA, we offer two type of software solution. We offer XNNC, which stands for Extensa Neural Network Compiler, and also ANN, Android Neural Network API. Extensa Neural Network Compiler is based on GLOW technology, and it has an ONNX interface, so we can support large number of framework like TF, TensorFlow, Caffe 2, PyTorch, and it offers a highly optimized code targeted at the Vision DSP and DNA product to run the neural network in a 8-bit integer. Android Neural Network API is required for Android, and for that we have what we call an online compiler that utilizes our XIANN library. Now, we've been talking about this compiler, XNNC, running with our Vision DSP and the DNA 150, but we have a large number of customers who use the Vision DSP and also uses their own custom AI accelerator. For that, we offer something called XNNC Link API to generate the code for their custom network, their custom AI accelerator. We'll talk a little bit more about that in the next slide. So XNNC Link, it's an NN code generator for your custom or your customer or our customer's AI accelerator. So as we talked earlier, our neural network compiler can support all these different Caffe tools, PyTorch, TensorFlow models, and the XNNC in general will work with Vision P6, Q7, and DSP. But if you are using our Vision DSP or our customers are using our Vision DSP and they have their own AI accelerator, then with XNNC Link, you could, with this API, one could define what layers should run on the custom AI accelerator and what layer should run on our DSP. So the combination of the Vision DSP and their customer's own AI accelerator can be used for the best AI performance. And the XNNC and the XNNC Link gives you the faster solution for this software. So we've been shipping this IP for a long time. So we have various customers already shipping our IP in various edge AI platforms. For example, MediaTek has been using us in their application processor for the mobile market and also for their IoT platforms. Toshiba for their autonomous or ADAS DSP, and a company called Neuron uses us for their KL720 platform. NXP and Baidu uses our Hi-Fi DSP for speech and voice AI processing. So here are some of the examples of our customers that we can publicly talk about. So in summary, voice AI and vision AI for edge requires pre and post processing in addition to the neural network processing. In addition to convolution layer, which are MAC heavy, other layers take considerable cycle. MAC operations acceleration only does not accelerate the AI performance. A combination of hardware acceleration for convolution and programmable DSP provide the best solution for edge AI workload. Single hardware can be used for both concurrent vision AI and voice AI workload. Cadence Tensilica provides vision plus AI and voice plus AI hardware IP with neural network compiler software. And we have a large number of customers shipping edge AI product based on our IP. Here are some of the references that you could use to look for our product. Thank you very much for attending this presentation.